Hi, my name is Quintas-Tang, and this is my project, the Arithmetic Logic Unit, or ALU for short. First, I'll do a brief overview on how the ALU works, then I'll explain the outer circuitry, and finally, I'll demonstrate some operations. The ALU is a combinational logic circuit, so it consists of many different logic gates all in this one chip. Seen on the screen is the block diagram for the ALU. The A0 to A3 and B0 to B3 are the two words that make up the input or data for the ALU. There's also the S0 to S3, which is the opcode. The opcode determines what functions the ALU will perform. Since there are 4 bits of data in the opcode, there are 16 different operations that the ALU can perform. However, this multiplies when the CN and M pin are added. This chart on screen shows every single possible input and output for the ALU, and I will go through each of them and explain how they work. This row to the far left is the S3 to S0 pins that are controlled by 4 switches on the breadboard. These control what operation the ALU is actually performing, but what operation they change depends on the M and SN pins. In this top row, it says active low data, which makes sense because all of the data pins are tied to ground through resistors. The ALU can perform 2 different sets of functions, logic functions and arithmetic functions. Logic functions are enabled when the M pin is high, and arithmetic operations are enabled when the M pin is low. However, for arithmetic operations, it depends on the CN pin. When the CN is low, there's no carry bit, and when the CN is high, there is a carry bit. If the row meets the M and sometimes CN conditions, which are above, that row is what the S0 to S3 bits control. If M is high, it's this row. If CN is low but M is low, it's this row. And if CN is high and M is low, it's the last row to the far right. Now, working our way down the column, let's say S3 to S0 is low, high, high, low, indicating this column, and M is low, and CN is low, indicating no carry. The function will be A minus B minus 1. But if, for example, this S page stays the same, CN is high, enabling a carry, F will equal A minus B. Now, onto the outer circuitry. There are a total of 16 switches on the breadboard, but only 14 are actually in use. The 2 switches farthest to the left are not being used. The 2 on the first 4-pin switch dip switch are the SN and M inputs. The second 4-switch dip switch are the S0 to S3 inputs that change the opcode. The farthest to the left is the S3, and it decreases sequentially to the right, ending at S0 as the farthest right. The next 8-switch dip switch is the A and B data inputs. A is the first 4 switches going from A3 to A0 from left to right, and the same as the S word, and the last 4 are the B data going from B3 to B0 left to right as well. Next is the actual ALU chip. On top of this is an orange LED. This connects to the CN plus 4 pin, and it turns on when the output of the ALU exceeds the maximum output length of 4 bits. For example, if the ALU output is 10,000, that's 5 bits of data and more than the output of the ALU can manage. When that happens, this orange LED turns on and tells me that this is occurring, and not that the answer is just 4 zeros. The next green LED is connected to the A equals 0 pin and is pulled high. This LED turns on when all of the outputs are high. It's not super necessary as you can just look at the outputs, but it's nice to have. Finally, there's all these LEDs in a row. These are all at the far right of the board, and there's 18 in total. The first 2 yellow LEDs are the mirrored output for the SN and M pins, and it tells us their status. Here they're off. If I switch them on, the LEDs turn on. The next 4 green LEDs are the mirrored outputs of the S0 to S3, and it tells us their status. The 8 red LEDs are the mirrored outputs of A to B data, with A being first, and it tells us their status. Finally, there's these last 4 green LEDs, and these are actually the final output of the ALU. I'll use the example from earlier to demonstrate the ALU in action. As you can see here, the S word is set to low, high, high, low. With M and SN both low, this indicates the function equals A minus B. We can see this works when I set A to 8, for example, and B to 1. The final output is 7 in binary. If I change the SN to be high, this changes the function to A minus B minus 1. And you can see here, with 8 minus 1, it equals 6 because of that extra minus 1. You can see here, if I also change it to, let's say, 4 minus 2, it'll do 4 minus 2 minus 1, which is just 1. Well, that was my video on the ALU, Arithmetic and Logic unit. Thanks for watching.